Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah, we meet again. So this is the last topic for this SEE 2423. Okay, topic number 4, which is electrical machine. So under this electrical machine, we will divide into what we call a DC machine and also AC machine. So for this topic, it may requires around maybe 2 weeks to complete this subtopic. Okay. So we will go for the overview of the motors, the principles of the DC machines. So why we call DC machine? Because a single machine here can operate as a DC motor, and it can also operate as a DC generator. So it is actually depends on the direction of the current. So if the current is going from the source to the machine, so it will be operated as a DC motor. But if the current is flowing from the machine into the source, so it will act as a DC generator. Okay, so in practical, there are several DC machine type. Is actually depending on the connection of the field circuit and also the armature circuit. Okay, so we have the shunt connected and separately excited DC machine, or right now we are concentrating on the DC machine as a motor. Okay, so that's why we call DC motor. Okay, and then we will go on the what they call the series connected DC motor. How to control the speed of the DC motor, and the last element here that we will actually teach you is on the DC generators. But these DC generators, we will only concentrate on the use of separately excited DC generators. And for your information also, we have several types of DC machine that is not covered in this syllabus. We have what we call the compound DC machine and so on. Okay. So at the end of this topic, for the DC machine, you should able to select the proper motor type for various application. State how torque varies with speed for various motor. Because in mechanical right now, we are now going for mechanical part. Okay. So in mechanical, there are two parts that are their main concern. Is actually the first one is the how many torque that can be produced, and how is the speed that can be produced by the motor. Okay, in electrical we have voltage and current as our main concern, but in mechanical especially for the machine, so they are more concentrating on the parameters such as torque and also speed. Okay, so actually in this subtopic, we will see the correlation or the relationship between voltage and current that will affect the production of the torque and also the speed. Okay, so the last one is actually we will actually develop what we call the equivalent circuit for the DC motor to compute its electrical and mechanical quantities. Okay, and we have also used the student need to know how to use the motor nameplate data and then understand the operation and characteristic of the shunt connected, series connected, and also I think shunt connected and series connected only. Okay, and another one is the series separately excited DC motor. So this is actually the general block diagram of the what we call electrical machine. So it is actually a component, okay, that relate the electrical and mechanical. So this machine, as you can see, can be a motor, and it can also be a generator. It depends on the energy flow, or it depends on the current direction. Okay, so if the current, if actually this one energy flow is from the electrical source into a mechanical, so this one acts as a motor, while if this one reverse from mechanical to electrical, so it is actually a generator. So as in general, an electrical machine is the link between electrical system and a mechanical system. So conversion from mechanical to electrical we call as a generator, while the conversion from electrical to mechanical we call as a motor. And in electrical machine, as mentioned before, we have two types, which is DC machine and also AC machine. Okay, so for AC machine, we covered maybe after maybe during week 14 and week 15. So for under this AC machine, we have the synchronous machine and also induction machine. So in this electrical machine, there are two electromagnetic phenomena that will occur inside the electrical machine. Okay, so this is the two electrical activities or phenomenon where when a conductor moves in a magnetic field, okay, a voltage is induced in the conductor. And the other one is when a current carrying conductor is placed inside a magnetic field, a conductor experiences a mechanical force. So there are two phenomena of electromagnetic that is actually happen that make the rotation of the uh, electrical machine is possible. So in general, electrical motor we consist two part, which is the stationary part, or sometimes also we call stator, and a rotor. So this rotor is actually the rotating part that connected to a shaft that coupled to the machine to its mechanical load. Okay, the shaft and rotor are supported by bearings so that they can rotate freely. This is actually illustrated in these figures. Okay, so we have the stator. Inside the stator, we have a winding. Okay, and then this is rotor, and as you can see, this shaft or drive shaft will be coupled with the with the mechanical load such as a tire or so on, okay, pulley or so on. Okay, and then we have the housing that has a bearing so that this rotor can actually rotate freely. Okay. So depending on the type of the machine, so either the stator or the rotor contain current carrying conductors configured into coil. Okay, slots are cut into the stator and rotor to contain the winding and their insulations. So current in the winding set up the magnetic field and interact with the field to produce the torque. So this is we'll cover further on how this interaction will produce torque. Okay. And this is the type of motors and their common applications. So for the AC motor, we have what called the three-phase AC motor. Okay, and then we have also an AC motor, a single phase. Usually for this single phase, they are usually used for our home fans, okay, water pumps, refrigerators, and so on. And this is also for the DC motors, okay, and we have shunt connected, series connected, and so on. And we have also what we call permanent magnet DC motor. So this permanent magnet DC motor is used for servo application, machine tool, computer peripheral, automotive fan, Windows motors, and so on. Okay, so but this one will not be covered in our syllabus. So exactly what is a DC motor? So DC motor are those that are powered from DC source. One of the difficulty with DC motor is that all electrical energy is distributed as AC. So if only AC power is available, so what we need to do is to have some rectification. So we convert AC power into a DC power, is DC voltage, okay? AC voltage into a DC voltage by using some some of the electrical circuit, for example, rectifier and so on. Okay, so actually, I have also share with you in my channel YouTube about a video, animation video about the DC motor. So I think it's better to have a look at this video. This is the link so that you have a better understanding and how we can actually convert and from electrical into a mechanical output. Okay. So that's why I think I just skip this. Okay, so I think you can refer to the video. Okay. So as you can see here, just for a comment here, so this is the stator, this is the cross section of this DC motor. So this is the stator and this is the rotor. And as you can see, the stator, they have their own winding, and also the rotor have their own winding. So just to make you know that for this stator, this is called we have the winding, and this winding after this we will call as a winding circuit, and this winding circuit here is used to produce flux, okay, to produce flux. And this is also used to magnetize this stator. So this stator is not a magnet, so it need to, if you want to magnetize this stator, okay, so you need to produce flux. So that's why we have winding here by using electromagnetic concept or theory to produce flux, so that we have south and north pole here, okay. And then this flux will actually interact with this conductor at the rotor side, and it will actually produce a torque. Okay, so it depends. So we have, this one is the 4 poles. The previous one is the 2 pole. So it depends on the number of pole. So the number of pole is actually depends on the stator. So we have 4. We can either have 8 or so on. Okay. And induced EMF. So what is induced EMF? So actually, if you notice, for a machine that rotate, so it will actually produce what we call back EMF. Okay, back EMF. So this is actually the this is actually a voltage that proportional with the speed. So if you increase the speed, the voltage induced inside the motor will also increase. Okay. Okay. So I think this one also is best described in the video, which is you can see from the video YouTube that I have shared. Okay. So I think I just go to the electrical circuit equivalence. Okay. So we have this one. We have several type of a DC motor. We have a shunt, series, compound motor. So compound, this one is actually a combination of series and shunt. So shunt is actually a parallel, meaning that the field circuit and armature circuit is connected in parallel, while series motor meaning that the field circuit and armature circuit is connected in series, while compound motor is the combination of series and shunt, while for separately excited DC motor meaning that your field circuit and armature circuit are separately connected separately. But for this syllabus, we only concentrate on shunt, series, and also separately excited DC motor. So this is actually the equivalent circuit of the DC motor. So this one is referring to the what we call the field circuit, and this one is a armature circuit. So field circuit is the circuit that refer to the stator. Okay. So this is actually stator, while the armature circuit is actually refer to the rotor. So the use of the field circuit is actually just to produce flux, okay? Because flux is actually proportional with the IF, the field current. So if you want to increase the flux, you need to increase the IF, okay? And usually, as you can see, for the field circuit, you have RF and also LF, okay? But if in a steady state condition, okay, we know because the voltage across the inductor, okay, is actually L dIF over dt. So if there is no change of current, so this one will become zero, meaning that the voltage across this inductor is zero. So usually in steady state, this one we can actually ignore this inductor, meaning that you can simplify your circuit as only contain RFs. Okay. For the armature circuit also, we also have actually inductor LA here. But since for the steady state, so the same reason in the steady state, usually in the there is no change of current, so the voltage across the inductor can be ignored. So that's why we actually can take out the inductor here. The effect of the inductor is actually very minimum. So that's why for the armature circuit, we have the only resistance, okay, and EA. So this EA is what we call the back EMF, and this is actually proportional with the speed of the motor. Okay, so the back EMF or the induced voltage is given by this equation. K, which is the constant, multiplied with the flux and multiply with the speed. Okay, so different value of speed will produce different back EMF. Okay, so if for example, if you want to know what is the voltage induced at different voltage at different speed, for example omega 2, you can use this relationship to get the voltage induced at omega 2. And then this is the relationship of the torque produced. Okay, so the torque produced by the motor is proportional with the current. So if you want to have a high torque, so you need to actually increase the armature current. And this one is the power developed by the motor from mechanical part. So the unit is same, which is watt. Okay, you can actually obtain the power developed by the motor equals to the speed of the motor multiplied with the torque produced by the motor. Okay. In other way, you can also compute the power developed by the motor by using this equation. EA, which is the back EMF, multiplied with the current IA. So actually, IA actually similar to omega of the speed of the motor multiplied with the torque of the motor. So the power rating of a motor is the output power that the motor can safely produce on a continuous basis. For example, we can safely operate a 5 horsepower motor with a load that absorbs 5 horsepower of mechanical power. It is important to realize that most motors can supply output power varying from 0 to several times, okay? Several times from their rated power, depending on the mechanical load. Okay, so it is up to the system designer to ensure that the motor is not overloaded. Okay, so actually this sentence shows that we can sometimes, not usually, okay, we can sometimes, several times, we can operate the motor over from its limit. Okay, but you need to be very careful. Okay, so please don't always overload your motor. Okay. So to have your motor operate safely, always that uh, to actually operate the motor at its power rating. Okay. So the power efficiency of the motor is given like this. So this is actually the general equation to calculate the efficiency. So well-designed electrical motor operating close to their rated capacity have efficiency in the range of 85 to 95%. Okay. Only on the other hand, if the motor is called upon to produce only a small fraction of its rated power, its efficiency is generally much lower. So it is always need to maintain the motor to operate at its rated capacity. Okay. If the motor is not if the motor is operated below than its rated capacity, usually the efficiency is very low. And this is the performance parameters for the motor. So the speed regulation. So depending on the torque speed characteristic, a motor may slow down as the torque demand by the load increase. Okay. Speed regulation is defined as a difference between the no load speed and the full load speed. Okay, and then it is expressed as this equation. So magnetizing curve. So what is magnetizing curve? So this is related to what we have already learned in our electromagnetic chapter or electromagnetic topic. Okay, so IF is proportional, as mentioned before. IF is proportional with the flux, and this EA is the back EMF voltage that induced due to the rotation of the motor, and this is actually correlated. So depending on the speed, okay, so we have for example, this is actually the curve, magnetizing curve, where the motor speed is around 1200 rotation per minute. So this is the curve. Okay, so depending on the speed, okay, so this is the speed for 1000 to, this is the curve for this speed. So from this for IF given this one, so it will based on this graph, it will produce 145 volt. Okay, we come to a example. The machine having magnetizing curve as shown in figure 16.15 is operating as a motor at speed 800 RPM with the armature current 30 ampere and the field current 2.5. The armature resistance is 0.3 while the field resistance is 50 ohm. Find the voltage VF applied to the field circuit, the voltage terminal applied to the armature, the developed torque, and also the developed power. Okay, so to find VF is very simple and straightforward because we already know that the circuit for the for the field circuit is actually contains VF, okay, and only a resistor. Okay, so from here we can calculate your VF. So IF is given to 0.5, RF is 50 ohms, so VF is 125. Okay, and then the next one is to get V terminal. So V terminal is the armature circuit. Okay, so IARA plus EA. Okay, so right now the speed of the motor is 800 RPM. Okay, 800 RPM. So, but right now EA for 800 RPM is we don't know. Okay, the only information that we obtain from this graph is 145 volt, but this is when the motor is rotating at 1200 RPM. So to get this VT, we need to find what is our voltage induced when the motor is rotating at 800 RPM. So by using the formula, the equation, the relationship of the voltage induced and the speed, so we can write this equation. So this is RPM. Okay, so this is the voltage induced at rotation 1200 and the voltage induced at 800. So based on this, finally we will obtain that the voltage induced at 800 RPM is around 96.7 volt. So right now we have already obtained this. So then we can include we can substitute the voltage EA with a 96.7. IA is 30 ampere, RA 0.3. So the voltage at the terminal of the armature circuit is 105.7 volt. Okay, and the developed torque. So the developed torque is equals to this equation. Okay, so K flux multiplied with IA. IA is already been given 30, but right now we don't know what is K flux here. Okay, so to obtain the K flux, the another information that we can obtain that we can use is actually this relationship. We know that EA is K flux with the speed. Okay, so what we want to do, what we need to do is from here, K flux. EA is given, okay, and the speed is also given. So I think we can use the speed of 1200 RPM. This one is 145. You can also use omega speed 800 RPM. Okay. Okay, but for this example, I use 1000 RPM. But you need to actually change into radian per second. So to change radian per second, what you need to do is multiply with 2 pi over 60. So based on this equation, okay, so finally I will obtain my K flux is equal to EA over omega, which is 1.15. So I obtain this one 1.15 multiplied with 30 ampere. So the torque developed by the motor is 34.5 Newton meter. Okay, and the developed power, you can always use this equation from the mechanical part, which is the torque multiplied with the speed. So I will obtain 2.89 kilowatt. You can also use power by using electrical parameters, which is EA multiplied with IA. So my EA is 96.7 multiplied with EA is 30. So by using calculator, I will obtain 2.9 kilowatt, which is actually similar to when using the power from the mechanical parameters.